Hi, my name is Caralyn Reisle, and I am a graduate student at the University of British Columbia in the bioinformatics program. Today, I'm going to be talking to you about robust variant interpretation in precision oncology using a graph knowledge base. Knowledge bases are curated databases of known and published variant information and their implications. They are a way of storing what we know from literature in a structured format that is programmatically accessible. There are a number of existing cancer knowledge bases, examples of which you'll see above. However, this is still not a solved problem. There are many challenges associated with knowledge base use and development. Most knowledge bases suffer from one or more of these. Integration into existing workflows is difficult due to the broad nature of their use and the many different types of variants involved. Free text and uncontrolled fields are difficult to understand programmatically and often contain errors. There are many competing standards amongst the various knowledge bases. And while most knowledge bases leverage ontologies as controlled vocabulary, few store the relationships along with the terms. This means that the end users must obtain the ontology themselves if they wish to leverage it in tools interacting with the knowledge base. Complex variants are often an afterthought. Support for variants like structural variants or molecular signatures are not given the same priority and level of detail in their data structure as the simpler counterparts, like the single nucleotide variants. Finally, scalability is always an issue. These unsolved challenges were the motivation for us to develop our platform for oncogenomic reporting and interpretation, also known as CORI. This platform consists of two major components, a graph knowledge base, GraphKB, and a reporting application, Integrated Pipeline Reports, or IPR. Today, we will focus on the graph knowledge base aspect. The CORI ecosystem consists of several servers and companion tools and packages. All of these are open source and can be installed by a Docker. The platform itself can be brought up from scratch using Docker Compose to organize the various containers. GraphKB is primarily used to annotate variants with their implications according to literature. Variants and patient data are collected, the variants are then matched against GraphKB, and the resulting content is aggregated and prioritized by the report loader before sending to the reporting application. Because GraphKB and IPR are highly integrated, we are able to motivate expedient entry of the most relevant content into our knowledge base. The analyst performing the review of a report in IPR can add any content they might come across not already in the knowledge base to GraphKB and regenerate the report in a matter of minutes. This provides a more targeted approach to curation. There are three main types of tables or vertices in GraphKB. The first is ontology terms. Nearly everything that is not a variant or a statement in GraphKB is represented as an ontology. The ontology model stores both the source of the term as well as its ID, name, and versioning information according to the source ontology. This ensures that it is traceable, and it also allows us to store multiple ontologies simultaneously. Here we are showing a number of different vertices which all correspond to KRAS. You can see that the Hugo gene is related to the Entree gene and the ensemble versions. Furthermore, we can store deprecated or old versions of a term. This is useful when importing content from older literature where the gene name used may be the older term. You can also see the gene related to its transcripts and proteins via this element of relationship, as well as the version of the transcript related to its unversioned counterpart via the generalization of relationships. By storing and relating all of these different possible representations of the same term, in this case KRAS, we can match our specificity and terminology to the source that it is pulled from. This avoids adding our own assumptions when the source is not specific enough to point to a particular transcript version, for example. The next vertex type to cover is variants. Our variant model is primarily defined by two different attributes: the type of the variant, or the variant classification, and the reference, or the gene the variant refers to. There are two different reference fields to allow for storage of complex variants such as fusions or translocations, where the variant may need to refer to two different reference sequences. As all three of these variants point to ontology terms, this model is easily generalizable to allow storage of other complex variants as well, such as molecular signatures. The final vertex type to cover are statements. These make up the bulk of the interpretive content in GraphKB. There are four fields of interest in our statement model. The first is the conditions. These are the conditions that must be present for the statement to apply. This can be any number of things, from the disease diagnosis, the detected variant, or a prior treatment. The subject and the relevance are used to distinguish the impact or the effect of the statement, and together we term these the statement conclusion. The subject, in this case, cisplatin, is the vertex to which the relevance, in this case sensitivity, applies. Finally, the fourth field is the evidence. This is the source that is used to support the rest of the statement, and most oftentimes it is a journal article, which we give by its PubMed ID. In the example above, we interpret this statement as saying, given a BRCA mutation and a diagnosis of breast cancer, we expect sensitivity to cisplatin. Here you can see what this looks like in the GraphKB client interface. Previous work on aggregating knowledge bases has been done by the Variant Interpretation for Cancer Consortium through their excellent meta-knowledge base project. There are some similarities between GraphKB and MetaKB as they aim to solve a related problem. While MetaKB is primarily focused on aggregation and standardization, GraphKB's main focus is on supporting matching and the consumption of uncontrolled resources. Both systems standardize the incoming data structure of the source knowledge base, and both support queries that leverage a graph and the ontology relationships. However, MetaKB standardizes the vocabulary and terminology of the incoming content to match a particular chosen standard, whereas GraphKB stores the content closer to its source representation. As GraphKB includes a web client with edit capabilities for users to interact with the data, it can act as both a standalone knowledge base, an aggregate of external knowledge bases, or any combination therein. There are some advantages and disadvantages to the approach taken by GraphKB. Some of the advantages are that we're able to match this level of specificity given by the source, which means we don't have to make assumptions when we're inputting. We don't need to transform the source vocabulary. This makes it easy to trace back from the version that is stored in GraphKB to the original version that's from the source knowledge base. This also simplifies matching and importing new resources because there's less steps to be taken. The disadvantages, however, are that it makes the database overall a larger size, and we still need to do some of the standardization or aggregation work after we're done with matching. To demonstrate the benefit of including multiple ontologies simultaneously, we're going to look at the task of importing or consuming clinical trials from clinicaltrials.gov. So the clinical trial records here have two fields of interest, the condition and the intervention, or in other words, the disease and the drug. These fields contain lists of drugs and diseases in free text and not using controlled vocabulary. So the initial challenge here is just the sheer number of terms. There are 581,000 different unique diseases and 298,000 different unique drugs. We chose accessible ontologies that are commonly used amongst the various cancer knowledge bases for the tasks here. In practice, first we would load the disease and drug ontology terms, and then attempt to look up the disease and drug terms for each clinical trial when we load the trials. You can see just from the numbers that there are many more disease terms in the clinical trials than there are in the ontologies, whereas the number for the drug terms are more similar. We make the distinction between total and primary terms for ontologies that include alternative names but do not assign its own ID. For example, a term in NCIT may be given as a single ID, but that IDs linked to several alias terms. The primary terms are the preferred or main name only, the one associated with the term ID. This is included as oftentimes only the preferred name will be used when the ontology is given or is set as a controlled vocabulary. We looked at the number of terms that were matched to an ontology representation across various ontology resources. We grouped the terms into 3 different sets based on how many different clinical trials that term appeared in, 1, 10, and 100. You can see above that the recovery for both term types is quite low in the first set. This isn't really unexpected as it includes all of the one-off terms. However, when we look at the more frequently used terms, those that appear in 10 or 100 or more clinical trials, the numbers become more reasonable. In the black bar, we are showing the union of all of the other resources. This is what we've labeled the combined set. This is effectively what would be stored in GraphKB because all of these ontologies exist simultaneously. While the gains in matching drug terms is marginal, the improvement in matching disease terms is much larger. The 9% gain represents more than 52,000 disease terms that would otherwise have been unmatched. Next, we're going to talk a little bit about how the matching algorithms that GraphKB uses work under the hood. The ontology matching algorithm heavily leverages the graph structure of our database, traverses the graph in 4 main steps. The first step matches a set of vertices based on the user's input query. Most often, this means matching vertices based on their name. Above, we have matched the vertex lung cancer. The next step, the query alias step, involves expanding the previously matched vertices to include equivalent terms. This means following edges bidirectionally, such as deprecated or aliases or cross-references. And we can see that this has resulted in including the alias term cancer of the lung. Now we'll give an example. The third step follows edges in a directed manner. It collects all of the paths along the inheritance-like edges, in this case subclass edges, where the path contains at least one of the previously matched vertices. It is important in this step that the edges are followed directionally to avoid inclusion of sibling terms. This means that we've now matched the terms solid tumors and small cell lung cancer, but not the term breast cancer. Finally, the aliasing step is repeated on the vertices collected in the previous step. To ensure that this process is really transparent, we've included an interactive view in the GraphKB client for users to visualize this matching algorithm with any input of their choice. They are then able to view the results through the graph view of the GraphKB client application, and this allows them to further explore and visualize the relationships between these terms. Using these ontology matching algorithms on the variant reference and type fields, we're able to robustly match many compatible representations of the same variant. Using KRAS G12D as an example, we can see that it has matched a less specific version where any mutation in KRAS will do, as well as a positional variant that encompasses a range. Finally, using the same matching algorithm we applied to the ontology terms, we expand this and apply it to the variant vertices, which is how we're able to match the genomic representation of this variant that is connected to the original via this infers relationship. The final feature of matching I want to talk about today is what we've dubbed second pass matching. So imagine we have a statement which says that KRAS G12D variant is a gain of function for the gene KRAS. And we have another statement which says that gain of functions in KRAS imply resistance to EGFR inhibitors. Logically, we can see that we should be able to infer that KRAS G12D results in resistance to EGFR inhibitors. This is really where the conclusion component of the statement model is so important. In GraphKB, we can effectively create a new variant using this conclusion, KRAS gain of function, which we then pass through in matching a second time. This allows us to capture these inferred statements, like KRAS G12D implies a resistance to EGFR inhibitors. This is quite powerful when your knowledge base has a lot of non-specific information. GraphQB is a robust and scalable platform. We've tested it on multiple sites, multiple users, and through multiple clinical trials. We've also tested it matching against externally generated data like the TCGA samples. In summary, GraphQB is a knowledge base that is able to integrate into existing workflows because it is part of a platform with support tools and documentation. It, along with the rest of the platform, is fully open source. It supports multiple ontologies simultaneously, as well as complex variants. We're able to use GraphQB to match non-specific variant notation, and it is a proven, scalable, user-tested platform. Thank you so much for listening. I will be leaving the rest of the time if there are any questions.